I'm talking today about Galaxy. Galaxy is kind of a sprawling project, and a lot of exciting things are happening on the platform. It's a sort of bioinformatics workbench. There's a data management system. There's visual analytics. And with all this excitement, I'm going to talk about the most boring thing I can, and that is how Galaxy sort of interfaces with clusters and work we're doing in this area. But there's lots of Galaxy talks at the ISMB, so hopefully you'll find something more interesting down the road. But we'll start here and we'll build, I guess. That's the plan anyway. So it will be kind of boring, but so what is my goal then? So my goal is to convince you that Galaxy runs jobs on clusters awesomely, and I'm including clouds here. I'm going to explain the whole process. I'm explaining that the whole process is pluggable, and existing plugins that we've written provide sort of useful functionality that you can leverage, and sort of make the case that writing new plugins for Galaxy, for Galaxy's execution engine, is sort of a great way to receive a potential wide usage and exposure for sort of innovative infrastructure work. So that's the case I'm going to make, I hope, or that's my goal anyway. And then, so ultimately, that's to convince you to leverage Galaxy as a platform with your next application, right? And so when I say leverage Galaxy, I think there are a few different ways to do that. The sort of most obvious, the most common way to leverage Galaxy is if you are a writer of a bioinformatics application, then a CLI, command line driven utility, then I encourage you to write your tools for Galaxy. There was always, Spades was a good example. Mentioned the tool shed. There's hundreds of applications in there. But even if you're going to build platforms or sort of do infrastructure work, I think extending Galaxy and leveraging Galaxy is possible there too. Some good examples of extending Galaxy include Globus Genomics, which is coming out of Chicago. It's a great platform for doing Galaxy on the cloud. There's over 50 public servers that sort of do this. And you can also leverage Galaxy via its API. So last year there was a really good talk at the Boston Refinery, which is sort of a beautiful application for managing data in a sort of semantically interesting way, building data sets, running Galaxy workflows on them, and then doing visualization afterwards. And so I don't think the users of Refinery would even know that it's Galaxy under the hood. So it's useful that way. Hopefully they find Galaxy useful. I know that them sort of building on top of Galaxy has been very useful for Galaxy, right? They pushed in a lot of great API enhancements and bug fixes. So very grateful about that. And then finally, I'm going to introduce Pulsar today, and it sort of lets you run jobs on clusters like Galaxy without having to deal with Galaxy's data model, right? So if you were writing your own pipeline package, for instance, hopefully you can leverage Pulsar to sort of run jobs like Galaxy. So in order to talk about the things we've been doing over the last year, I'm going to talk about the traditional Galaxy execution model just as a sort of baseline for what we've done and how we've made it a lot better. So generally, typically, Galaxy's tools is an XML concept that sort of describes the UI and how to build command lines for applications. These commands, Galaxy will then execute them on clusters or locally, and then the deployers of Galaxy, the system administrators who are deploying this, describe the resource requests for that cluster, so how many cores, how much memory, etc. And the files are accessed directly by Galaxy in the commute node. So we're breaking down these three limitations, and I'll talk about this and other things we're doing in this space. So where can Galaxy run jobs? So a lot of different places. We were deployed at many institutions, so there's a lot of work there for getting this to talk to different clusters. Drama is a common way to do it, but there's other specialized ways. Any sort of queuing system that has a command line process for submitting and monitoring jobs can be integrated. We're doing work with Mesos and running Galaxy and Docker containers, and we'll talk about this too. So one thing Galaxy is very good at, I think, given that we have a lot of tool developers and a lot of people who are deploying Galaxy, is there's sort of separation of concerns there, and sort of keeping these two groups happy, hopefully, and sort of giving the tool developers, the tools they need to write applications for Galaxies, but then letting deployers sort of adapt it to their environment. And so, yes, ideally, a single Galaxy instance can be, set up to submit to many different clusters and heterogeneous resources that are available at different institutions. Coming at this from the deployer perspective, Galaxy's always sort of had this concept of being able to write plugins to contact the job resource managers. But more recently, the second point here is you can now write plugins that define how you route jobs. So it's not a static mapping from this tool always is going to run on this cluster with these resources, right? So now deployers can write dynamic plugins to route jobs based on input parameters, which user is submitting the job, group associations, etc. In particular, so we call these enhancements dynamic job destinations. And just in the last couple months, we've added the ability for deployers to sort of delay jobs. So if they want to set up custom limits for researchers at an institution, they can. Deployment-specific parameter collection. So tool authors have always had the ability to sort of specify what tools or what parameters their tool takes and map them. And now deployers can inject their own parameters into this user interface so that they can allow users to say which queue they want to submit to or what sort of resources they want to use. And then they can consume this in a sort of dynamic fashion that's specific to the institution. And so again, this is coming back to sort of a separation between the tool author and the deployer. And we've added some ability now. Well, we'll talk about job metrics in a little bit, but to sort of some high-level utilities for tracking, resource usage, so that users or deployers can, build prioritization schemes and I think there's. At a lot of institutions, I know the previous institution where I worked, there's only so much compute to go around, and bioinformaticians really love to just use it all. So we're giving tools to let the institutions do this fairly, hopefully. That's the idea, anyway. So we've added dynamic state handlers. So the idea here is just if you submit a job to a cluster engine and you run out of memory, the job runs out of memory or hits the wall time limit, the deployer can now specify rules for what to do in that case. So we recently moved our public server from Penn State to the Texas Advanced Computing Center, TAC. And we now have a lot of different resources available to us. So we have a dedicated cluster, and we also can submit jobs on the big shared cluster there. But this big shared cluster, it takes 2 days to get your job to wait, right? So we don't want users to have to wait 2 days. So our plan is, or what we're going to do is, we'll run it on the local dedicated cluster for Galaxy. Give it a maximum wall time of 2 or 3 hours, and if the job can't finish, we'll then let the cluster engine kill it and resubmit it elsewhere. So this gets back to some of these sort of really boring issues, right? Like if you're writing infrastructure, you don't necessarily want to have to deal with all of this, and hopefully Galaxy is here to sort of deal with these problems so that you can sort of think at a higher level. But we're sort of working through these issues, and hopefully you don't have to if you leverage Galaxy. So all of that was about how jobs get routed, but even once you've got a command and it's running on the cluster, there's a couple more things we're doing in this space. So Galaxy for a long time has had this concept of packages, but we've recently added a sort of plugin infrastructure to let you sort of define how these packages get resolved on your local cluster. Traditionally Galaxy has had the ability to sort of say, well, this tool defines that it requires BWA, say, and the deployer can specify how to load BWA in the environment. We're trying to move more towards the tool shed and having automatic installation and setup procedures so that deployers just click a one button install and get everything they need. But that's not the, this isn't necessarily everybody's answer. There's different institutions are going to have their own things, right? So as part of this plugin mechanism, we've added recently is the ability to tie into Linux modules. So if you have a large shared cluster and you have a bunch of software set up, you can tie Linux module systems into Galaxy quite easily. And then that's that's packages, right? But there's this exciting concept that's gaining a lot of attention right now in sort of boring computer infrastructure space, and that's this idea of containers like Docker. So we've recently added pluggable container resolution. So what is Docker? It's a lightweight runtime and packaging tool that allows you to run the same app unchanged on laptops. 5 minutes left, or 5 minutes? Okay. VMs in any cloud. So it enjoys the sort of resource isolation and allocation benefits of VMs, but is much more portable and efficient. So Galaxy can now run tools in Docker containers. Tool authors may declare what images they're compatible with. Deployers can specify, which destinations at their institution have Docker enabled and how to exploit it there. We have this concept of job metrics, which again are pluggable. Some simple examples: job runtimes, cores allocated. All of this is the plugins instrument the job and then feed the result into the Galaxy database. Those are the simple examples. A more sophisticated example is CollectL, is a plugin that we've written for the job metrics system. It's capable of producing sort of per process level breakdowns of many different things, different kinds of memory usage, different kinds of CPU usage, an estimate of I/O consumption, and Galaxy can sort of record these detailed logs for offline playback using CollectL, or it can sort of in real time, as the jobs are completed, process them and collect statistics and record them. Again, it's a plug-in infrastructure, so you can write your own. We got this shared file system problem in Galaxy. Traditionally, it's sort of assumed that you have a large shared cluster. We've recently, we're trying to get away from that with Pulsar. It was formerly called the LWR. Briefly brought it up at last year's BOSC, but it's grown up a lot since then. Then it was useful for sort of running jobs on one-off remote servers, kind of to address proteomics applications, where you've got some applications that only run on Windows, for instance. But today it's running jobs in some of the most well-known supercomputers in the United States, at least in academia. So it's got a new RESTful API, all these new features, a lot of these new features I mentioned in terms of the plugin support are useful within Pulsar. It can talk via message queues, so you don't have to plug in, so you don't have to break firewalls in order to sort of submit jobs. So to make it more useful in more different kinds of scenarios, deployment scenarios. And it also has this concept of file actions. So the reality of sort of file systems at large institutions can be complex. Different file systems are mounted in different places. And they have different properties, right? And so one way to address that, some things in this space address that by sort of centralizing everything, right? So sort of transferring everything in a uniform fashion. But Pulsar lets you sort of define different paths and have different kinds of staging actions. So it lets you optimize data access for your particular deployment. And Mesos is like Docker, has a lot of, it's very popular right now, and some big names are using it as a sort of parallelization framework. Spark was brought up earlier. Spark can run on Mesos. And Pulsar can now sort of act as a Mesos framework. Just want to say thanks to the Galaxy team. My former employers at the Minnesota Supercomputing Institute helped funded some of this initial work on the LWR deployment, and big thanks to the Galaxy community for sort of building awesome stuff and pushing the platform forward. Are there any questions?